Welcome back to ECE 220. Group A, last two sections are finishing up your labs today and tomorrow for lab number 2. That's sections G and H. Group B, or section I, your pre-lab for lab number 2 is due on Saturday. And everyone has a homework assignment due on Tuesday of next week, and we all have our second exam on Thursday. A week from today, we will be doing round 2 on exams, and exam 2 will be covering chapter 4 material, which is consistent, or that's what we were using in homeworks 4, 5, and 6. Today what I want to do is continue with op amps, which is chapter 5 material, and you could start looking ahead to chapter 6, which is now introducing another element, circuit element, or elements, and that will be capacitors and inductors. And those now allow us to do energy storage, and those will give us more interesting dynamical behavior than resistors do. But today what we want to do is look at the input resistance in op-amp circuits, Thevenin equivalents at the output, so we're sort of looking at input-output properties of these op-amp circuits. How do they look to a source? How do they look to a load? How do they appear? And then we'll start maybe preparing for exam number 3 by looking at finding variables in op-amp circuits. Now I might ask you to find a given variable, and you now need to walk through the steps in our analysis process to try to find that variable of interest. And then, depending on how far we make today in terms of progress, what about this realistic or more realistic model of an op-amp? We've been assuming ideal conditions, and I hope when we get to that more realistic op-amp model, the analysis will expand in terms of complexity, but the end result is about what we've been doing with the ideal op-amp assumptions. That's the bottom line. Let's then look at what these op-amp sources might look like. Two sources, TO sources, and we'll be using two sources, TWO sources at times, but we will be looking at them individually. If we're looking at the input resistance in op-amp circuits, we're asking this question: what is the resistance seen by a particular source, or in this case by our voltage sources that we are applying to the circuit? And here is example number 1. And that should make you feel very comfortable, this circuit, by this point in our discussion of op-amps. That is a very classic inverting amplifier interconnected circuit. The non-inverting terminal is connected directly to ground, and we have two resistors, the input resistor R sub S, the feedback resistor R sub F, and an applied voltage, which I'm now calling V sub A. And here's what I'm wanting, and we can sort of look at this before I scroll further down on the page. We can look at it generally. We can say, what is R sub I? And don't get confused, we have too much overuse of variables, so let me try to make this a little bit, I'll really make it clear. I now marked it in red. Let's say this is input resistor as seen by source A, R sub IA. We will have R sub I as the resistance of our op-amp circuit, so don't confuse that with what I'm saying here. Here we're saying, what does this voltage source, V sub A, what resistance does it see as it looks in to this particular circuit. But we can start analyzing that with strategies that we've been developing throughout the course. First, let's just say that for this analysis, let's just assume that we are dealing with an ideal op-amp. And what's the next item of interest on your piece of paper or on your circuit that you need to make clear to yourself that's happening in this interconnected op-amp? What's the first thing you want to be looking for? Probably. Yes, if we're by a fire and we have our hand going towards the fire, are we retracting? Do we have feedback? And when we're driving, we have feedback, right? We're watching the road and we're adjusting our vehicle's position, or if we're on a skateboard or if we're on a bicycle, we are always using feedback. So it's no surprise then that what we design might have feedback incorporated in it as well. And a subsequent class will play with feedback. Not only your electronics classes, but a 441A, a technical elective. Maybe that's a couple of semesters away, but that involves feedback. Big component of that class. And any control class that you might take. I'm not sure where that commercial came from. Anyway, R sub I sub A, seen by V sub A. How would you describe, or could you come up with an expression that might allow us to calculate R sub I sub A? What would that be? This is now the resistance looking into that circuit as if we were V sub A. We're now looking at it from the reference node or the common node and the positive node of V sub A, and we're looking into that circuit. How could we describe R sub I sub A? I forgot to even follow up. Man, I made that commercial and I got sidetracked. What was I trying to suggest? You're thinking of feedback. Is there feedback in this circuit? And it's negative, so now we have negative feedback, which is a good thing. That now allows us to say that we're going to assume that the inverting and non-inverting pins of this op-amp circuit are at the same potential. And here we can actually see that the non-inverting pin is connected to ground, so that's already equal to 0. Or that's our common. The expression that I was begging for R sub I sub A is V sub A over I sub A, where this is now I sub A. That's now the effective resistance that source sees. It's now the voltage across those two terminals divided by the current into that terminal. That's Ohm's law, and that's really what we are trying to determine here. Can you now find I sub A? We know V sub A, that's given. That's sort of like our test source that we've been talking about when we looked at Thevenin equivalents. V sub A you could view as a test source, but now it's a generic V sub A. What is I sub A? Is I sub A 0? And that's a reasonable thought, and why are you making that? Because it's kind of connected to the inverting pin of our op-amp, right? And we said the input impedance of these op-amps are really, really big, and consequently then the current going in, so we can say that here, I sub P is equal to 0. And we can say it where else? Right above it, on the right side of that node. We can only say that this, I can't even write that small, I apologize, but this current I sub n is equal to 0 going here. So that one is 0, but I sub a, not necessarily, because it has other places it can go. But what do we know about the other side of that, the right side of that resistor? We know the left side is at a potential V sub A. What do we know about the right side of resistor R sub S relative to its potential or its voltage? Based on feedback, that commercial, we have negative feedback. So it's the same potential as the non-inverting pin, which is at 0. Now we know the voltage dropped across that resistor. It's V sub A minus V sub n, V sub A minus 0, divided by the resistance, and that will give us our current. We now can say that I sub A is V sub A minus V sub n over R sub S. But this was 0 because of this and the fact that V sub P was equal to 0. Or we now have V sub A over R sub S, and now we can write down the answer to the question, what is R sub IA, or R sub I sub A seen by V sub A? That's now V sub A over I sub A, which is V sub A over R sub S, which is, in fact, R sub S. The resistance seen by that voltage source is not the input impedance of our op-amp, which could be 2 megohms. That's right at the pins. We've now connected some external resistors around this op-amp, and in this case, our resistance seen by that source V sub A is in fact R sub S. Questions on that? Was that clear what we were doing? And we could then put it into this if we wanted to. Now we could say, oh, if you give me particular values for R sub S and R sub F, now the input or the resistance seen by the voltage source V sub A is 10K. That was fairly clean. Let's now look at example 2. And again, let me try to distinguish that resistance, be a little bit more specific. Let's say that that's R sub I sub B, the resistance seen by source V sub B. Well, and let's just assume that this is an ideal op-amp. We're waiting until the end to get to more realistic op-amp circuits. But as I said at the beginning, we'll find that it's not that much different. When we do all of this full-blown analysis, we'll end up with about the same answers as we're getting, assuming ideal op-amp behavior. What's one thing about an ideal op-amp in terms of its behavior? Just as sort of a refresher. What are we assuming? What are some conditions for the ideal op-amp? What are the assumptions that we're making? No current flow into the input pins of the op-amp, and that's because in the ideal case we're assuming infinite input impedance at the input pins. Here this question is a little different, isn't it? We're asking for the resistance seen by the source, not directly at the input pins. The amplification, the open loop gain, capital A, we're assuming is going to infinity. And we're assuming that the output resistance of this op-amp is 0. Those are the three main points of an ideal op-amp. What do you want to now note about this circuit? Or we could say, oh, well, I don't know, he's asking for R sub I sub B. Let me see if I can get partial credit on a multiple choice exam. R sub I sub B, is equal to, well, if it's what we were talking about before, can't I just say it's this if this is now I sub B? Isn't that how I defined the resistance seen by the previous source? What is I sub B here? This one is 0, isn't it? And what's that mean? Well, and this is because I sub P is equal to 0, and where I sub B is exactly the same as I sub P. That's directly connected to the non-inverting pin of that op-amp. Even though we have a source there, it's not supplying any current because the input impedance is infinite on the pins of the op-amp, and we're connected directly to that pin through that resistor R sub C. What's that mean R sub I sub B is? Ooh, V sub B divided by 0. That's not allowed, is it? Well, let's let that I sub P get small in the limit, or I sub B. So that means that R sub I sub B, since infinity technically isn't a number, I'm not going to say equals. I'm going to say R sub I sub B approaches infinity. Infinity is out there. Can't really reach it. But it's huge. Now, no matter how we've connected this, do these numerical values for the different resistors matter? For the resistance seen by source V sub B in this connection? No, it's still infinity. First one was 10K. Now we're up to infinity. Let's look at some more. Example 3. And we won't go quite to the numerical values just yet. And what am I doing? Let's go ahead and make this a little bit more specific. Let's say R sub I sub B seen by V sub B. Can my formula for R sub I sub B be the same as it was in example 2? Isn't it still supposed to be V sub B over I sub B? That's R sub I sub B. Why did you put this example in? We just did it. Not quite. Do you see the difference? This is slightly different and significantly different from example 2. Example 3 now has another resistor in between R sub C's right side and the non-inverting pin, input pin of the op amp. Is I sub B equal to 0? Well, it was before. Why isn't it now? Don't ask me. You guys tell me. You'll be out maybe doing an internship this summer and somebody might say, what's going on here? And you'll go, well, let me tell you what's going on here. Right? How much of a lecture do you want? Maybe you wouldn't phrase it that way. Maybe you would say, I don't know, don't take any advice from me. All right. This isn't being recorded, is it? What is I sub B? Can we find it? Is everybody comfortable saying that I sub B is not equal to 0? Why? Because R sub what? Yeah, so I sub B has a path to go to, doesn't it now? It doesn't see an infinite impedance only. It now has another lower resistant path to the common node. R sub D is now there for I sub B to flow. There's no current going to go into that non-inverting pin of the op amp. But there's a junction there, and it can go to the path, well, in this case, the path more traveled, because the path not traveled is into the op amp. There's nothing going in there. It's too difficult to go. The impedance of the resistance is too high. What is I sub B then? Can we calculate it? This is a review for the final now, because it's what we did in exam number 1. If I said find I sub B, can you tell what I'm asking you to do? I'm covering it up. Can you cover up all the circuit except the sub-circuit for the source and the 2 resistors it's connected to? And then that common node is really connected. You now just have one mesh. You can now find the current in that mesh. That current in the mesh is what I'm asking you to find, which is I sub B, and that's now V sub B over R sub C plus R sub D. What does that mean R sub I sub B is? We're still using this formula, V sub B over I sub B, but I sub B has V sub B in its numerator. We get a cancellation and we have the sum of those 2 resistors in the denominator of the denominator. They now come upstairs, or this now becomes R sub C plus R sub D. And if we wanted to now compute that numerically, given these values, we could now say, oh, the resistance seen by source B now in this circuit is 33K plus 47K, which is 80K ohms. That's a little different than infinity, isn't it? But we've made a change in our circuit. What I'm saying is on exam 3, you're going to have to be very observant, very focused on what you're seeing or what you're given as a circuit to analyze. Example 4. which one am I? Okay, let's now say R sub I sub A. Come on, you gave me this before. Wasn't this, what was this? Well, not quite. Now it's interconnected a little different, and now I have a voltage source, two different voltage sources, one connected to the inverting pin and one connected to the non-inverting pin. And I don't know that I said it last time, I was just assuming it. We're assuming an ideal op amp again. And we have the necessary feedback. We have negative feedback, which now allows us to say that V sub P is equal to V sub N, or that's what we'll assume, and then we'll check what happens later. After we get the result, we would then say, are we in saturation or not? Here's V sub P, and here's I sub B if we need it. What is I sub B? That one's 0 now. We don't have another path for it to go to. And for that reason, what is V sub P? V sub P is, in fact, V sub B, because there's no voltage drop across that resistor R sub C since there's no current flow. So I sub B equaling 0 allows us to say that V sub P is equal to V sub B, and because of the negative feedback, that's equal to V sub N, which is right there. That's V sub N. So now, can we calculate I sub A? Because R sub I sub A, if we're keeping the same understanding, the same relationship, it needs to be, okay, I'm injecting a voltage and I'm going to measure the current that I get out, and that ratio is going to give me the resistance that that particular source sees. What is I sub A? In terms of some of the labels I have on the diagram. And not just some, the correct labels that I have on the diagram. What is I sub A? Correct. Did everybody catch that? It's V sub A. It's where we are. And this depends on the direction that I've labeled I sub A. Now I have it going through R sub A to the right. It's now V sub A minus V sub N over R sub A. And if we wanted to put numbers to that, I've given you so many numbers here. V sub A is now 0.67 volts. V sub N is V sub P, which is V sub B. Ooh, the world. So now we have 0.67 minus 0.8 over R sub A, which is 10K. Oh man, This is what happens when you make these this lectures up a little late in the evening. I don't know if anybody looks at the timestamp. I hope not, but if you had to stay up a little later last night to see this last night. It was posted a little late. So what do we have here? I sub A. What's the sign of I sub A? S-I-G-N. It's negative. Ooh. So it's, in fact, going in the other direction to what we have labeled. Now we have current flowing back into that source, V sub A. And that's possible because we have two sources here. And we actually have four sources. Do you see the other two? I think he's still asleep. Where are our other two sources? They're on the rails, right? So we have to be powering this, and sometimes we get a little sloppy and then we forget. But this poor op amp, in order for it to even work, has to be energized with power supplies, and those aren't even shown here. You now have to have a V++ or a VCC, a VEE at the negative power pins of this op amp to make it work. It's not even being shown, and we would have to say what that is if we wanted to check if we were in saturation. But now what we've learned is that, in fact, this current that I've labeled in the direction I sub A is not going in that way if we interpret the sign here. It's actually, the current is in fact going into the A voltage, V sub A, which means we're charging this source in a sense. So all bets are off with this calculation. What are we getting for R sub I sub A? It's now V sub A over I sub A, and V sub A was 0.67, and I sub A is negative. And did I compute it? I think I just wanted to give up. Here it's minus 13 times 10 to the minus 6. It's not very big. It's in the microamps. Hopefully I've done the calculations right. And this becomes minus 51,538 ohms. That just means that if you now increase the voltage, your current's going to decrease. If you increased V sub A, your current is going to decrease. So this is kind of a non-standard, non-inverting amplifier configuration because of the way that the voltages have been specified. So this is a little confusing, so don't lose sleep over it. Just compute it. So this one, let's just say, is not a standard. And the reason it's not standard is you probably aren't going to be designing this, in this case, to be charging your voltage sources. You probably want your voltage sources to be helping the circuit perform instead of going the other direction. So not a standard non-inverting amplifier circuit, because V sub B is supplying power to V sub A. Maybe not what you would want to design. Let's look at a fifth example, which is really kind of how that fourth example appeared. What's the difference between this one, example 4, and example 5. I apologize, I'm kind of scrolling through those quickly. Did you see the distinction or the difference? Just start reciting your ABCs and put those ABCs as subscripts on your R's. And in the first example 4, I think I ran out of letters, didn't I, when I got to C? Vanna wasn't turning it over any more letters. Nobody even knows what I'm talking about. Wow, I'm dated. Huh. Now we have R sub D, and we didn't have it before. I don't think. R sub D was not there. Now we have a different scenario. Do you see how just kind of one change can make things quite different? In example 4, our I sub B was 0. Now I sub B is non-zero because it has a path to flow to the common node through R sub D. Let's now look at what happens at those two different voltage sources, V sub A and V sub B. But does everybody now see what we have? What kind of an op-amp circuit is this? Do you remember? And we've drawn it a couple of different ways. Now we have V sub A going through like a normal inverting op-amp. V sub B looks more like a non-inverting, so we are combining those. This is that difference amplifier that we were talking about. So now we have a difference amplifier, and we might want to ask, what are the resistances seen by these two different sources? Let's see what we can uncover. So the parameter values are the same, I think, as what I had for example 4. 10K for R sub A, R sub B was 100K, R sub C was 33K, and R sub D was 47K. V sub A and V sub B, which were giving us fits last time, are going to be the same. And we're explicitly reminding ourselves of the fact that this op-amp is energized through the rails, through the power supplies, and those are at plus and minus 5 volts. Let's now look at part A, which is what's the resistance seen by source V sub A. And if you were looking for partial credit, what would you do? And I would do this just because you don't need to keep all of this stuff in your head. You know, people ask, do I need to memorize this stuff? Not necessarily, and you might want to just take notes so your brain isn't having to try to remember everything. You can kind of think about the solution. You know this is available to you when you need it. What's the formula for R sub I sub A that we've been using all morning? I gave you half of it. Now it's over I sub A. And let's now go back and see what we have here. And before you get too far into this, you might just say, well, wait a minute. Is there a path for I sub A to proceed, or is it trying to slam into a high impedance or a high resistance wall? In this case, you could have a non-zero I sub A. It's not necessarily 0, so you have to proceed. If it was 0, let's say I eliminated R sub B, then it would be 0. And then what would the impedance seen by V sub A be? If I now erased R sub B, what's the impedance seen by V sub A? Infinite, right? Because there's no current, so it looks like an infinite impedance that it would be seeing. But here that's not the case. And let's just assume that we have an ideal op amp and negative feedback. We're not assuming that. We have negative feedback, so this allows us to assume that V sub P is equal to V sub N. And here's V sub P. And where's V sub N? It's not as neat as V sub P, is it? It's kind of splattered around. It's this big thing. That's now V sub N. It's a blob, but it's still there. Each of those wires are connected to the inverting pin of the op amp. And now with negative feedback, we're going to assume that we have a virtual short between those two. They're at the same voltage. What were we wanting to do? Nothing. Well, let's go beyond that. Now we have R sub I sub A that we're trying to find. Can we find I sub A? I sub A is now V sub A minus V sub N over R sub A. What's V sub N? Now it's not connected virtually to ground, is it? Or to the common. It's equal to V sub B. And it's equal to V sub P. What is V sub P? Go back to exam 1. What is V sub P? Can you calculate it even if you don't remember? It's a voltage divider, but if you don't remember, you can say, well, let me just do KVL and compute what the voltage dropped across R sub D is once I find that mesh current. If you do that, you'll see that that's just a voltage divider, and now we can use that to let us keep going here. Now we know that we need V sub N, but V sub N is equal to V sub P by the negative feedback, and V sub P is R sub D over R sub C plus R sub D times V sub B. And if we plug in these numbers, this that we're given above, this is about 60% of what V sub B was, and V sub B was 800 millivolts or 0.8 volts. V sub N now becomes 0.47. So we were about 60% of 0.8, not quite, and that gives us then V sub N being 0.47. Now I sub A is going the direction that we assumed in our labeling. I sub N is now the 0.67 minus the 0.47 over R sub A, and wasn't that 10K? This is now 0.2 divided by 10,000, or 0.2 times 10 to the minus 4, or 2 times 10 to the minus 5. Or 20 microamps. That's I sub A, and now that allows us to find the resistance seen by voltage source A is V sub A over I sub A, and V sub A was the 0.67. This is now 20 microamps. And that now ends up being 33,500 ohms, which is not R sub S, which was 10K. It's not 2 meg, which is the impedance at the input pins of your op-amp. It's something different because of the way this op-amp is interconnected. And now you can say, oh, if I need to connect a source, and if you're in the lab, what did you have to do to get your function generator to work the way you are expecting it to work? What was one? Well, you had to do a lot of things. First, you had to turn it on. But after you turn it on, you now need to put it in the high Z mode. So it's expecting to see a high impedance at its output. Well, now this voltage source A, is expecting to see 33.5 k ohms. What's source B expecting to see? What's R sub I sub B? Now we have I sub B here. What is I sub B? Do you see it? Can you now start to just kind of intuitively sense what's happening? I sub B is not 0, is it? I sub B is V sub B over the sum of those two resistors, R sub C plus R sub D, and R sub I sub B is V sub B over I sub B, and I sub B was V sub B over R sub C plus R sub D. And if we in fact plugged in the numbers, source B sees something different in terms of resistance than source A. And it's interconnected more directly to different resistors, so you would expect that. We went through quite a few different circuits to try to find what does each source see as it's looking into this amplifier circuit, this op-amp circuit. And we were coming up with different values throughout. They aren't all the same. They're not all just as easy as this very last one that we just calculated. What if we wanted to look at the other terminals? What if we now want to look at the output side of this op-amp circuit? We now want to say, well, if I'm trying to put a load on the output pins of this op-amp circuit, what will I expect my load to see if it's looking back and seeing a Thevenin equivalent? What will it see? That's the question that we're asking now. Before we were saying, what if I plugged a source into the input side of these op-amp circuits? Now we want to know what's happening over here. What does it look like looking back into the circuit from the output side? Can we find a Thevenin equivalent at those two terminals? And if we're doing Thevenin equivalent, then you might be saying, well, I need an A and a B to talk about Thevenin equivalent. Now we're saying, what's the Thevenin equivalent between terminals A and B? And what thought process can we use? Again, I'm assuming this is an ideal op-amp. And that should just start awakening all of these different steps. What's the next step in your process? Feedback. Is there feedback? Yes, and it's negative feedback. We haven't talked about positive feedback yet, but we'll get there, I guess. What's today? Thursday. We'll get there tomorrow. It tells me right here, I just need to look, I guess. I don't have this. Wow, really? So what do you expect this to be for its Thevenin equivalent? If you just had to quickly guess, what would you say its Thevenin equivalent looks like? And this, I think we mentioned at the very beginning of the discussion of op amps. We said that it would look like an ideal voltage source. It's not even going to have any internal resistance. It's not going to have an R Thevenin. Its R Thevenin is 0 in the ideal case. And what's its voltage going to be in this? This is an inverting op amp. It's going to be a negative voltage, but that's what our Thevenin equivalent will be. It's huge. It's now minus 90 times V sub G, but that's the Thevenin equivalent, and we'll pick up there on Friday.